In this recording, I'd like to go through some of the useful example extra friction problems that we didn't have a chance to go through in class. I thought this would be useful for studying. In the first problem, we have an example of an incline with a pulley. This is a massless pulley, and there is friction. So it's the same system that was described in lecture 10, but this time the coefficient of static friction is 0.2 and the coefficient of kinetic friction is 0.1. And the question is, what happens when this system is released? As always, the first step is to draw the free body diagrams for the two masses. Now, in this particular picture, we're drawing them sort of connected to each other on the same graph, but you don't have to do that. The red and blue are both independent free body diagrams. As you recall, the blue mass experiences two forces, mg pulling down and tension pulling up. The orangish block experiences tension pulling diagonally parallel to the surface of the incline. It experiences a normal force, and it experiences its mass, which is 2m times gravity, that force pulling directly down. Now, we are going to make an assumption here, but as I always like to point out, whatever direction we assume to be the positive direction, it's okay. Even if we're wrong, we'll just get a negative answer, and that'll tell us it's going the opposite of what we think. But we're going to posit that motion without friction, well, we know that motion without friction is going to progress this way from the problem that we did, problem 10. And so we're going to define our positive x direction as up for the blue block and down to the right diagonally for the orange block. Now, the net force along the direction of motion without friction for the orangish block is going to be 2mg sine of 35 degrees minus mg. So that's the net force, and that is going to be equal to 0.15 mg. The maximum static friction force is going to be equal to mu sub s times n. So now we need to calculate what the normal force is, and what we're trying to determine here is, does this system move at all, or is the static friction large enough to keep it in check? And given that the net force on the block is 0.15 mg, if mu sub s n is greater than 0.15 mg, then the static friction will be large enough to balance the 0.15 mg, and therefore the block won't move. So let's plug in the numbers. The normal force is going to be 2mg cosine of 35 degrees, and we multiply that by mu sub s, and we ultimately get 0.33 mg. The static friction is actually larger than the net force applied to the orange block, and so the block does not move. This is actually a static case. So whereas this would have moved without friction, the static friction is large enough to hold the block in place. This top hat problem is a really good way of understanding static friction, and so I'd like to go through it. I'm going to give you a couple seconds to think about it. The question is, what is the magnitude of the static friction force in the system that we just studied? Is it A, 0.15 mg, B, 0.33 mg, or C, 0.4 mg? I'm going to give you a moment to think about that. If you need more time, feel free to pause. Otherwise, I'm going to move on. The answer is 0.15 mg. Now, you might think, well, wait a second, mu sub s times n was 0.33 mg, isn't it 0.33 mg? The thing to remember about static friction is mu n sets the upper limit of the biggest that the static friction can be. But static friction by definition is always as big as it needs to be to balance the forces. And since the net force on the orange block is 0.15 mg, the frictional force has to be equal and opposite 0.15 mg to hold things in the static case. Again, you can never have a situation where the static friction is larger than the other net forces on the object, because then by construction the object would accelerate, and friction is not the sort of force to do that. So the answer is 0.15 mg. It is as large as it needs to be. The point, though, is that if the net force on the block were bigger, let's say it was 0.2 mg, then the friction would be 0.2 mg. And this would continue until we reached 0.33 mg. At that point, that we're approaching the limit where the net force, if it was just a little bit bigger, is too big for the static friction. And then at that point, we would be in a regime with kinetic friction. So for a system to be at rest, F sub s needs to cancel out the net force without friction. Option C is obviously beyond the maximum possible value, as we'd said, which was 0.33 mg. And option B would produce a net force to the left, and that would be a non-physical situation. Let's do another example. A 49-kilogram rock climber is climbing a chimney between two rock slabs. The coefficient of static friction between her shoes and the rock is 1.2. Between her back and the rock is 0.8. She has reduced her push against the rock until her back shoes are on the verge of slipping. What is her push against the rock? So let's draw the free body diagram. Her weight is pulling down. There are the two normal forces from the two surfaces, one pressing against her foot and one pressing against her back. These are going to be equal and opposite because she's pushing with one force against the wall, and that's pushing her back against the other wall. There's going to be the friction due to her feet and the friction due to her back. Now, the friction forces will potentially be different, or not potentially, they will be different, precisely because the coefficient of friction for her feet and her back are different. But what matters ultimately is the sum of the two friction forces, which balance out her weight. And this is, of course, a static situation. So we have that the normal force minus the normal force equals max, and there's no acceleration in the x direction, so that equals 0. It's two equal and opposite normal forces. In the y direction, we have the friction on her back and the friction on her feet minus mg, her weight, equals may, and this again is a static situation, so the sum of the two frictions minus mg has to equal 0. In other words, the sum of the two frictions has to be equal and opposite to her weight, mg. If n is large enough, both forces will be less than mu sub n. As n decreases, as she decreases the normal force, the maximum static friction will get closer and closer to the actual value of the friction needed to balance her forces. Eventually, n is going to be just enough so that the total static friction is exactly equal. The maximum static friction is equal to the static friction, which is equal to her weight. If the climber pushes less than this, the friction will not be enough to compensate. And so what we do here is now we assert that the limiting case, the smallest possible normal force, is the one where mu sub s times the normal force for her feet and back is exactly equal to mg. If she applies a larger normal force, again, the maximum friction will be larger, but the actual friction will always be mg. So we plug this in, we solve for n, we get mg over the sum of the two coefficients of friction, and we get 240 newtons. Let's do another problem. We've got a box on a truck. The box has a mass of 50 kilograms and it sits on a truck. The coefficients of friction between the box and the truck are mu sub k equals 0.2 and mu sub s equals 0.4. What is the maximum acceleration that the truck can have without the box slipping? So let's take a look at the diagram. we have the normal force and the weight in equal and opposite directions. And those always have to balance, because if the box is sitting on the bed of the truck, then obviously there's no acceleration in the y direction. In the x direction, the static friction is what's going to hold the box on as the truck moves forward with an acceleration a. Now, I will qualify that here, in a sense, the friction is accelerating the box, but not in that weird non-physical way where you imagine the frictional force is larger than the net forces on the object and the object slides. But you can have static friction hold an object in place while it's sitting on something that's moving, and then that is the way in which it gets pulled forward. And so there's going to be a static friction force that is going to be resisting the tendency of this block to stay in place, and it's going to be going in the direction of the acceleration of the truck and the block, assuming that the coefficient of static friction holds. Of course, if the truck goes fast enough, your physical intuition will tell you that the block will slip. So we have, of course, that the normal force minus the weight equals 0. But the other equation is there's really only one force acting on this block. So the truck is accelerating. Why does the block accelerate with the truck? Because the static force, the static friction, which is the relative, the force between the block and the surface it's sitting on, that is going to pull the block with the truck. So the net force, F sub s, has to be large enough to equal the mass of the box times its acceleration. And therefore, the maximum static friction needs to be equal to the mass of the box times the maximum possible acceleration. So A sub max, the maximum acceleration that the truck can take, is going to be equal to the maximum static friction divided by the mass of the box. And so we can write that as mu sub s n over the mass of the box. And since, of course, the normal force is equal and opposite to mg, we have mu sub s mb times g divided by mb. The masses cancel out, and we get that the maximum acceleration where the box will move with the truck is mu sub s times g. If the truck accelerates faster than that, the box will not go with the truck. It'll kind of slide. It'll slip. The truck will go forward. The block will not go forward as much. And it'll eventually fall off the bed. But as long as the acceleration of the truck is below mu sub s times g, the box will travel with the truck. So, and when we calculate that with the actual values, we get that the fastest acceleration that the box can handle before sliding around is 3.9 meters per second squared. One more example. A box of mass m1 equals 1.5 kilograms is being pulled by a horizontal string with a tension of 45 newtons. It sits on top of a second box of mass m2 equals 3 kilograms, which in turn sits on a frictionless floor. There is friction, mu sub k equals 0.5, and mu sub s equals 0.7 between the two boxes. And we want to find the acceleration of the two boxes. So we are applying tension to the topmost box. The free body diagram for the topmost box has the tension pulling to the left, and the frictional force is oppositional, and so it's going to be moving to, or not moving, the friction force is going to be pointing to the right. And the key thing here is that if there was no friction force and we were to tug on the blue block, it would just move and it would slide over the second mass, and it would do nothing. Without friction force, there's no way for mass 1 to pull mass 2. That's the direction of the friction force that mass 1 sees. So mass 1 is going to see the oppositional friction force from the surface between mass 1 and mass 2. Mass 2 is going to see the corresponding Newtonian reaction, which is mass 2 is going to see the friction of mass 1 pulling it to the left. And this is the mechanism whereby, in principle, mass 2 is going to pull mass 1 is going to pull mass 2 along for the ride. So first, let's assume that the boxes move together. Now, we don't know that that's the case. It may very well be, and this is kind of thinking along the lines of the previous problem, it may very well be that if we pull with too much force on block M1, it will slip, that the static friction condition will be broken. Notice, by the way, this is a moving problem, and the truck bed was a moving problem, but the friction was static friction. Why? Because the static is referring to the relative motion of the two surfaces. In the static case, the surface of the blue block will be on top of the orange M2 block, and their surfaces will not move with respect to each other. They will be fixed together. That is static friction. Slipping is where you go into kinetic friction. Now, we don't yet know whether or not the static friction condition is met, but let's assume first, for the sake of argument, that it is. Well, if the static friction holds, then we know that the ultimate force pulling on the system of two blocks is the tension, and so the acceleration is going to be equal to the mass of both blocks times the acceleration that they're doing together, and therefore the acceleration of both blocks, which is the same, is going to be equal to the tension divided by the combined masses, and that works out to be 10 meters per second squared. Now, armed with that information, we can now calculate the static friction condition. So M2 moves because of friction, and the static friction is going to be equal to M2 times its acceleration. So what is pulling block M2? The static friction. So that's our net force is going to be F sub s, and that's going to be equal to m sub 2's mass times its acceleration. This is just a statement of Newton's law applied specifically to the orange block. And so what we end up getting is that the static friction, in order for M2 to be pulled with an acceleration of 10 meters per second squared, the static friction needs to be 30 newtons. The maximum allowed friction force for static friction is going to be equal to mu sub Sn. So if mu sub Sn is greater than 30 newtons, then the static friction will be 30 newtons. It will be as large as it needs to be, and the two blocks will slide together. If the maximum friction force is less than 30 newtons, then if I'm tugging on the blue block, it's going to slip, and it's not going to really pull the orange block with it. So let's do the math. From box 1, we know that the normal force minus m1g equals 0. So we know that the normal force is equal to the mass of block 1 times g. And so now we can calculate the static friction maximum by multiplying the coefficient of friction times the normal force, and we get 10.3 newtons, which is indeed less than 30 newtons. So the static friction is not enough for the boxes to move together. The way that this problem is set up, given the tension force of 45 newtons, it's going to end up breaking the static friction condition, and the blue block is going to slide. So the boxes do not move together, and in this case, the friction is kinetic. So if we write the Newton's second laws for the two blocks, what we have is that the first block is going to see the tension force pulling it to the left and the kinetic friction pulling it to the right, and that's going to be equal to the acceleration of the first block times the mass of the first block. Notice that this time the two blocks are actually accelerating with different rates. Box 2 only sees one force. It sees the Newtonian pair, the corresponding friction force to the left, and that net force is going to be equal to the mass of block 2 times its acceleration, which is now different from the acceleration of block 1. And we know that the kinetic friction is going to be equal to mu sub k, not mu sub s, times n, and we know that the normal force is m1g. And so when we solve this system of two equations, we end up getting that the first block is going to accelerate with 25 meters per second squared, while the second block is going to accelerate at 2.45 meters per second squared. So it's not as if the second block stays still. The act of the top block sliding across it, in applying kinetic friction, does apply force to accelerate block 2. But most of the acceleration is taken up by block 1 since it is moving and there's not the static force holding them together. Remember, typically in problems that you're doing with, or not typically, but in many cases in problems you're doing with blocks, especially if the blocks are pressing against each other, then they are accelerating together. And so you can always assume that the acceleration of the two blocks is the same value, A, full stop. In this case, because of the previous slide, where we established that the static friction is not going to hold. In other words, the blue block's surface is not going to be fixed with respect to the orange block's surface. We're going to be in a sliding condition. Because of that, it's necessarily true that the two blocks are not going to be accelerating at exactly the same rate. And as you see, we calculated what their two accelerations are. That is the end of these example problems. I hope you found them useful, and I hope they help aid you in your studying.